Now, section 15.7 is all about optimization for functions of two variables. We're going to break it apart into section A, which is going to deal with relative maximum and maxima and minima, and then section B, which will be for absolute maximum and minimum. All right, so let's look at relative maxes and mins. Now, we've done this in Calc 1, so we're going to expand upon what we learned in Calc 1 into Calc 3. So in Calc 1, we learned that over here we have a relative max, and over here we have a relative min. Now, there are a couple ways that you can find that. So you can find it with the first derivative test. The first derivative test is when you take the first derivative, you set it equal to 0 or it is undefined, right? 0 or undefined, i.e. your critical values, and then you test those critical values, right? You analyze them. And one of the ways to analyze them, there are other methods that we learned, but the most common way is to use the second derivative test, right? So we take those critical values, we place them into the second derivative. And if the second derivative is positive, then the function has a minimum at that point. If the second derivative is negative, then it has a maximum. And if it's equal to 0 or is undefined, then we are inconclusive. Okay, so we will expand upon that just with more dimensions. So over here, we have a maximum, let's say here, and a minimum, we'll just say is down here, right? Just for the sake of, because we're thinking of a particular region, right? So you have a maximum and a minimum, and they're at values x comma y, right? So or C1, C2. So you find the critical values where the derivative with respect to x and the derivative with respect to y are equal to 0 or undefined. So just like we did in Calc 1. So we'll take where is the derivative, but it has to be both derivatives, equal to 0 or undefined at that spot. So it has to be that it's both at the same time. That will be a critical point. And then we take those critical values and we put them into the second derivative, sort of, right? So it's a little bit more complicated. So we'll have d defined right here. It's fxx, fyy minus fxy squared. And we're going to evaluate it at the critical points. So if d is greater than 0, but the function is, actually, and fxx is greater than 0, the function has a minimum. If d is greater than 0, but fxx is less than 0, then it has a maximum. If d is less than 0, then it has a saddle point. And if d is equal to 0, it's inconclusive. All right, so basically it's the same as what we did in Calc 1, just a little bit more expanded. There's a little bit more going on, of course, because there's more dimensions and more things to keep track of. All right, so let's do an example. All right, so fill in the chart for the following. At a critical point of the function, z equals f of x, y, where fx equals fy equals 0, define d. Okay, so d is fxx fyy minus fxy squared. And what we're going to do is rewrite this table here, and then we'll get to the example. So if d is positive and fxx is positive, then we have a minimum. If d is positive and fxx is negative, so positive then negative, that's a maximum. If d is negative, that's a saddle point. Which, if you remember what a saddle point is, if you think of a saddle, right, hyperbolic paraboloid, right? So a saddle point is a minimum in one direction, but a maximum in the other direction, right? So let me write that down. There we go. So it's a minimum in one direction, but a maximum in the other direction. My end got cut off there. All right, so that's what a saddle point is. And then if it's 0, the test is inconclusive. All right, so now let's get to that example. So first thing we have to do is we have to locate our critical points. We don't know what they are off the top of our heads, so we're going to have to find our critical points. All right, well, to do that, critical points will be where the derivative with respect to x and the derivative with respect to y are both equal to 0 simultaneously. So let me just make a note. fxx and fyy are both equal to 0 at same point. Right? 0 or undefined. Right? Undefined. Undefined is not going to happen in this particular problem. So, all right, so fx would be the derivative with respect to x, which is 4x cubed minus 4. That's it, right? So everything else is 0, right? And then fy would be 4y cubed minus 32. And that both of these have to be equal to 0 simultaneously. Or technically undefined, but undefined is not going to happen because these are polynomials. All right, so how can I make that happen? If this one only has x in it, so I could actually solve for x. I could add the 4. So x cubed is 1, so x is the cube root of 1, which is 1. And over here, this would be equal to 0, so 4y cubed would be 32, y cubed would be 8, y would be the cube root of 8, which is 2. And it has to be both of these things simultaneously, which is going to work out just fine, because neither one of these had the other variable in it. So our critical point is 1, 2. Now technically there's a z over here that I never bothered to find, but I mean I could go find it, right? Something, right? So z would be equal to 1 to the 4th plus 2 to the 4th minus 4 times 1 minus 32 times 2 plus 10, which is what, 16 take away 4 is 12. Oh, sorry, 1 plus 16 is 17. 17 take away 4 is 13. 13 take away 64 plus 10 is negative 41. Okay, so negative 41 is the z. Okay, now we have to make the table. So the way you make the table is you say the critical point, which is 1, 2, negative 41. A lot of places don't bother with the negative 41 right there because it's not strictly needed to do all of this, but if you want it, there you have it. So if you want to just say 1, 2, that's also fine. All right, now what about d? Now I don't need, what d is, I just need its value, whether it's positive or negative, but I'm going to have to find that in order to be able to do it. All right, so d is, let me write this down here. fxx would be the derivative of fx with respect to x, would be 12x squared. Fyy would be the derivative of this piece with respect to y, which again would be 12y squared. fxy, there is no y in this, so it's 0. So putting these together, d is fxx times fyy minus fxy squared. So let me write that down. fxx times fyy minus fxy squared. Okay, so that would be 48. Oh, excuse me, bigger than that. So 144. 144 x squared y squared. Okay, so now we have to think to ourselves. If we put 1 and 2 in there for x and y, what's going to happen to d? Well, it's going to be positive, right? Because 144 times 1 squared times 2 squared is a positive number. And I don't actually really care what the number is. I just need to know what sign it is. All right, now I need to know about fxx because this is positive. I need to go back and see, okay, if it's positive, what about fxx? Well, fxx is right here. It's 12x squared. So if I put 1 into that, 12 times 1 is positive. So it's a positive positive, which means that the conclusion would be that z equals f of xy has a minimum at 1, to negative 41. And just so you can see this all, I did it all in Maple as well. Maple will find FXX and FYY, no problem. So I had it do that. But then if you look at the surface right here, so you can see, oops, it was upside down for a second. But there you have it. So that value right there, 1 to negative 41, is the minimum right there. I made the point into that box down there so you could see it better. So our graph is backing up our conclusions that we had a local minimum at that spot.